Hello, in this problem we will calculate the size of a star given its temperature and luminosity. The relevant relationship that we're going to use for this problem is that the radius of a star is equal to the square root of the luminosity divided by the temperature to the fourth power. This relationship comes from basically the idea that luminosity of stars depends upon their surface area and also their temperature. Basically, the hotter stars are, generally they are brighter. The bigger stars are, in terms of their radius, generally the brighter they are as well. If we put this together, area of a sphere, since stars are spheres, is 4 pi r squared. And the temperature part comes from Stefan's law, which says that the amount of radiation leaving each little part of a star's surface depends on a constant, sigma, times temperature to the fourth power. Now we can get rid of these constants, the 4 pi and the sigma, if we're going to express L, R, and T in terms of values of the sun. And the law then simplifies to L equals R squared times temperature to the fourth power. And if we solve that relationship for R, then we get what I started with here, that the radius is equal to the square root of the luminosity over temperature to the fourth power. So here is a little problem then with some values that we can plug in. Typical of an intro level problem involving stellar radius. So we have a star that is 3 times the temperature of the sun. The sun's temperature is about 6,000 Kelvin, so that'd be 18,000. But we're going to use the T value in terms of comparison to the sun, so we'll need 3. And luminosity is about 100,000 suns, or sorry, 100 suns. So we need to solve then for R, put the values in the formula, square root of 100, then over 3 to the fourth power, which happens to be 81. Simplify it a little bit. So then we need to go ahead and do the arithmetic on that. So on a scientific calculator, 100 divided by 81 is equal to roughly 1.235. So we're going to need to take the square root of that. You'll want to use the complete number that you would have in your calculator to get a more precise value. But it's basically the square root of 1.235. And so when we go ahead and take the square root of that, we find that the answer is about 1.1, repeating. So 1.1 times the radius of the sun. So it's just a tiny bit bigger than the sun in terms of radius in this example.